Now today we will discuss on stereoisomerism. So what is the stereoisomerism? In which compound having same molecular formula but different arrangement of atoms in a space, different arrangement of atoms in a space is called as stereoisomerism. Different arrangement of atoms in a space is called as stereoisomerism. Now, the stereoisomerisms are two types. Stereoisomerisms are two types. Number one, configurational isomerism, and number two is conformational isomerism. So these are the two types of stereoisomers. So today we will discuss on this configurational isomerism. So what is meant by the configurational isomerism? So first we will discuss on this configurational isomerism. Configurational isomerism. Now this configurational isomerism are two types. Number one is geometrical isomerism. So first is geometrical isomerism. Now what is my geometrical isomerism? The stereoisomers. Stereoisomers which cannot interconvert, at room temperature due to restricted rotation is called or is known as this geometrical isomerism. Stereoisomers which cannot interconvert at room temperature due to the restricted rotation is called the geometrical isomerism. And then second type is optical isomerism. Second type is optical isomerism. Stereoisomers which have different behavior. Stereoisomers which have different behavior towards plane polarized light is known as optical isomerism. So these are the two type of conformational isomerisms. So first we see what is meant by. So geometrical isomerisms, stereochemistry which cannot interconvert at room temperature due to restricted rotation is called as the geometrical isomerism. Now what is the condition for geometrical isomerism? Condition for geometrical isomerism. Only those compounds shows geometrical isomerisms in which double bonded carbon atoms have different atoms of groups. So what is the condition? Only those compounds shows geometrical isomerism in which double bonded carbon atom attached to different atoms or groups. What is the main condition? Only those compounds show the geometrical isomerism in which this is double bonded carbon atom attached to different atoms or groups. Now, for example, now this C double bond C. Now this is A, B, C, and D. In this compound, this double bonded carbon atom attached to the different atoms or groups. This double bonded carbon attached to the different atoms or group. But in this example, this double bonded atom attached with the same atoms or groups. Therefore, this compound does not show the geometrical isomerism. So this does not show geometrical isomerism, and this shows the geometrical isomerism. So what is the main condition? This double bonded carbon atom have the different atoms or group on which is the main condition for the geometrical isomerism. Now which compound shows the geometrical isomerism? Now alkenes C double bond C, oxides C double bond NOH. Also compounds N double bond N shows geometrical isomerism due to restricted rotation about double bonds. Why these alkenes, oxides, and other compounds show the geometrical isomerism? Due to restricted rotation about the double bond. Cycloalkanes shows geometrical isomerism due to restricted rotation restricted rotation about single bond in ring. So these compounds, these three compounds, alkenes, oxime and azo compounds, show the geometrical due to the restricted rotation about the double bond, and cycloalkanes show the geometrical due to the restricted rotation about the single bond in ring. Now, the nomenclature system in geometrical isomerism. Nomenclature system in geometrical isomerism. Now, there are two types of nomenclature systems. So, number one is cis-trans system. Cis-trans system. So, first nomenclature system is the cis-trans system. Now, in the cis-trans system, if compound having two similar group on the same side of the double bond, called cis isomer. And if compound having two similar group on the opposite sides of the double bond, then it is called the trans isomers. Now, for example, C double bond C. Now this A, B, and this is also A, B. So in this example, two similar groups are at the same side of the double bond, therefore it is called the cis. And if now this is A and this is B, now this is B and this is A. Now in this example, two similar group. Now this two similar group, this A and A similar group on the opposite side of the double bond, therefore it is called the trans. It is called trans. Similar, these two A group are on the opposite side of the double bond, therefore it is called the trans. For example, C double bond C. Now this CH3 is H, CH3 is H, and this is a cis compound C double bond C. Now this CH3 is H, CH3 and this H. H and this is the CH3. Now these two similar groups are on the opposite side of the double bond, and therefore it is called the trans isomer. This is called the trans. So this is the first nomenclature system, that is the cis and trans. Two similar groups on the same side of the double bond is called the cis, and two similar groups on the opposite side of the double bond is called the trans. So two CS group, in this example, two CS group on the same side of the double bond is called cis, two CS group on the opposite side of the double bond is called the trans. So second type of system of nomenclature is EZ system of nomenclature. Second is the EZ system of nomenclature. Now first, what is meant by E? So E means, this is the name of scientist Entgegen. Entgegen. It is the Entgegen, in which when high priority group on the opposite side, then it is termed or it is denoted by E. And third means Zusammen. When high priority group, that means the Zusammen, when high priority group on the same side of the double bond, then it is denoted by thread. So this is the AZ system of nomenclature. For example, now this is the high priority group, and this is also high priority group. This is the low priority and this low priority. Now their high priority group are on the same side of the bond, therefore it is denoted by thread. If their high priority group are on the opposite side of the double bond, then it is denoted by E. So this is an example of EZ system of nomenclature. Now for the EZ system, there are sequence rules. To determine the geometrical isomerism. So there are the sequence rules for geometrical isomerism. So first rule, so rule number 1, sequence priority of the atom. Sequence priority of atom or group. Sequence priority of atom or group at carbon is decided on the basis of atomic number. That is, priority is directly proportional to this atomic number. Now, for example, now this C double bond C, this iodine, Br, Cl, and this F. Now, in this case, this iodine having atomic number 53, bromine having atomic number 35, this 17, and fluorine 9. Now, in comparison between two atoms or groups, there this iodine atom having the higher purity, it having the higher purity, and this having the lower purity. In between these two atoms, this chlorine having the higher purity and fluorine having the lower purity. So these higher purity group are on the opposite side of the double bond. Therefore, it is the E configuration. Now, this C double bond C, this is the F, Cl, this I, and this Br. Now, this I having higher purity, this Br having lower purity, this having lower purity, and this having the higher purity. Now, in this example, their higher purity group are on the same side of the double bond. Therefore, it is denoted by Z. So, this is the rule number 1. Rule number 1, the sequence purity of atom or group at carbon atom is decided on the basis of atomic number. That is, the purity is directly proportional to atomic number. So, this is the rule number 1. Now, the rule number 2. Rule number 2, if purity cannot be decided by, if purity cannot be decided by rule number 1, purity cannot be decided by rule number 1, it is determined by comparing next atom. Comparing next atom. So, for example, this F, this CH2CH3. Now this CH3, this CH2, this CH3. Now in this example, first atom is carbon and we have fluorine. Fluorine having atom number 9 and carbon having 6. Therefore, this fluorine having the higher purity and this ethyl group having the lower purity. Now in this case, the first atom is carbon and first atom is carbon. Therefore, we cannot decide the purity as per the first rule. Therefore, this CH3 is equivalent to this C. The second atoms are H, H, and H. Now, in case of CH2CH3, their second atoms are now this C, H, and this H. Now again this C is ring row, it's 3 hydrogens. So this is the C, this CH3 and 2H are these. So first carbon atom, in this case this first is atom is the carbon, second atom is hydrogen here, second atom is carbon. Therefore this CH2CH3 having the higher purity than this carbon. In this example, the higher purity group are at the same side of the double bond. Therefore, it is denoted by Z. The another example, the C double bond C, CH2CH3, and CH, the CH taken twice. Here F, CH2, CH3. Now this having higher purity than this CH2, CH3. Now in this example, first atom are carbon. So we can write this CH2, CH3, which is equivalent to now this C. Now this CH, and this CH, CH3 taken twice is equivalent to now this C, this H, this C, this C. So in this example, that the CH3 and CH2 is compared like this. The CH3 is written here, second atom is hydrogen, hydrogen, and this example the second atom is carbon. Therefore, this CH2 CH3 group has the higher purity than the CH group, and in this example, both higher purity group are at the same site. Therefore, this is the third configuration. And in this example, there the CH2 CH3 is right like this, and this isopropyl group CH3 taken twice is right. Now the second atom is carbon. Here second atom is carbon, but in ethyl group the second atom is hydrogen. Here second atom is carbon. Therefore, this isopropyl group has the higher purity than this ethyl group. Therefore, this configuration is the E configuration. So when purity cannot be decided by the rule number 1, that is determined by the comparing the next group. So these are the next group compared with the 1 atom. So this is the rule number 2. Now the rule number 3. Rule number 3. If doubly or triply bonded atoms, doubly or triply bonded atoms is equivalent to 2 or 3 atoms, 2 or 3 atoms attached or linked to the carbon atom, For example, now this R, C double bond O. We can write this R is as it is, but this C is double bonded carbon atom. We can write this, but this double bonded means doubly bonded atom is equivalent to 2 atoms. So this doubly bonded atom is equivalent to 2 atoms. The another example is R C triple bond N, which is equivalent to this R C. Now we can write this N 3 times. So triply bonded atom is equivalent to 3 atoms linked to the carbon. Now for example, now this C double bond C, there this CHO and here C double bond OH. Now this is the NH2 and C triple bond M. C triple bond M. So this is an example. Now in this example, the first atom is carbon and nitrogen. Therefore, this nitrogen having higher purity and this carbon having the lower. Now in this example, the first atoms are the carbon, but second atom are. Now this CH group is equivalent to. Now this C, we can write this double bonded oxygen 2 times and then this H. Similarly, in case of COOH, we can write this C, this double bonded atom 2 times and then OH. So in CHO and COOH, the second atom is oxygen. Yes, in COH second atom is oxygen. Second atom is oxygen. Here also second atom is oxygen. But here second atom is hydrogen and here second atom is oxygen. Therefore, this COOH group having the higher purity than this CHO group. The CHO group having the lower purity. Therefore, higher purity group are on the same side of the double bond. Therefore, this configuration is called the third. Now, this is the third configuration. Now, another example. Another one example, a simple example is C double bond C, the COOH, and this is the CH3. Now this CH3 and this H. Now this has a higher purity and this has the lower purity. Now in case of first atom R, carbon atom. Now the CH3 is equal to CHHH. Second atoms are hydrogens. Now in case of COOH, which is equivalent to C, the second atom are oxygen, oxygen, oxygen. Therefore, this having a higher purity than this CH3. Therefore, higher purity group are on the same side of the double bond. Therefore, it having the third configuration. So this is the rule number 3. Now, rule number 4. Rule number 4. If isotopes of the same elements, if isotopes of the same element, isotopes of the same element are attached the isotopes with the isotope with higher mass number having higher purity. So what is the rule? If isotopes of the same element are attached, then isotopes with higher mass number having the higher purity. So for example, now this C double bond C, here D H, now this H and then CH, D H, this H and this. Now this CH is having higher purity, this having the lower purity. Now in this case, this atomic number of hydrogen is 1, atomic number of deuterium is 1, but mass number is 2 for the deuterium. So this isotope having the mass number 2, therefore it having the higher purity. So it having the higher purity and this hydrogen having the lower purity. In this example, higher purity group are on the opposite side of the double bond. Therefore, it is the E configuration. Another example of the C double bond C. Now this is the H. Now this CH3 and H. Now this 1, 2, this is 1, 1. So this is the higher purity group and this is the lower purity group. This is the higher purity group and this is the lower. So higher purity group are on the same side of the double bond. This is denoted by the set. So this is the rule number 4. If isotopes of the same element are attached, then isotopes with higher mass number having the higher purity. Now, the rule number 5. Rule number 5. If in a compound, one of the double bonded atom, one of the double bonded atom does not having any substituent, then that vacant position is considered to have atomic number zero. Atomic number 0. For example, benzyl dioxide on the C double bond this N, this OH. Now this is C6H5 and this H. Now this is the vacant position, no substituent. That is the atomic number is 0. Atomic number is 0, therefore this is the low purity and this is the high purity. This is the low purity and this is the high purity. So high purity group are on the opposite side. Therefore, this is the E configuration. Now, second example is acetal dioxide. Is similar of the CH3H. Now here no substituent. Now this position is a vacant position, therefore there is a no substituent. This is the vacant position and therefore their atomic number is considered to be the 0. Atomic number is 0. This oxygen having atomic number 8. This atomic number is 0. Therefore, this OH group having the higher purity and this having the lower purity. This CH3 group having the higher purity and this H having the lower purity. So, higher purity group are on the opposite side of the double bond. Therefore, this acetal dioxide having the E configuration. Now, azo compound. Now in this azo compound there N double bond N, there is C6H5 and there is C6H5. Now this is the vacant position and this is also the vacant position, therefore here is a no. Now this is the vacant position and this is the vacant position, that is the no substituent, therefore the atomic number is 0. Atomic number is 0, therefore this having the lower priority, this having the higher priority. Now here no substituent, atomic number, there atomic number is 0, therefore this having the higher priority and this having the lower priority. So higher priority group are on the opposite side, their conservation is E conservation. So this is the fifth rule. If in a compound one of the double bonded atom does not have any substituent, then that vacant position is considered to have atomic number 0. Now in this example, this is the vacant position. This is the vacant position. Now this is the vacant position. This is the vacant position. And this is the vacant position. So vacant position is considered the atomic number is 0. Therefore it having the lower priority. Now the geometrical EZ system or geometrical isomerism is side coordinates. Geometrical isomerism in cycloalkane. Now in this cycloalkane, the disubstituent cycloalkanes or dimethyl cycloalkane is Q1. In the C-sign transform, if both methyl group are on the same site, then it is considered to be the cis isomer. And if these two methyl group on the opposite side, then it is a trans isomer. So these cycloalkanes also show the geometrical isomerism in the this geometrical isomerism shows in the C-sign transform. So this is the geometrical isomerism, one of the type of